Okay, we're going to get started here because we do have a limited time and a lot of content to cover. Hello, everyone, and welcome to our first session of the 2022-2023 Forest and Climate Learning Exchange Series. I'm your host, Catherine Maloney, and I'm the private sector liaison with the Forest, Carbon, and Climate Program at Michigan State. As you can see here, we had previously, there's the speaker lineup for the rest of the year, and you can find more information on our website, which we have dropped in the chat. Next slide, please. I want to give a quick thanks to our co-host, the Society of American Forests, or SAF. SAF is the national scientific and educational organization representing forestry and related natural resource professionals across the United States. Founded in 1900, SAF promotes science-based, sustainable management and stewardship of the nation's public and private forests. Similarly, a thank you to our additional sponsors, NCS and Renew West. For today's presentations, we'll be discussing innovative approaches to forest carbon management and modeling. First, we will hear from Mark Bradford with the Forest School at Yale School for the Environment about estimating forest carbon storage in the city. And after that, we will hear from Colin Beier from SUNY ESF about mapping and monitoring forest biomass and carbon stock change across complex landscapes. Thank you both for joining us today. Before we get started, we'll do some quick housekeeping. First, to automatically receive registration details and information regarding upcoming webinars, please join our mailing list by emailing forestc@msu.edu. A recording of this session along with a copy of the slides and any supplemental resources will be posted to our site. After the presentations, we will host a Q&A session. We ask that you submit questions via the chat or Q&A function at the bottom of the Zoom interface. You can do so at any time during the presentation, and we will do our best to address as many questions as possible at the end. I know sometimes people are required to just call in by phone and don't have access to that chat. If that's so, feel free to email us again at forestc@msu.edu, and we will add that to the pool of questions. Starting with our next session on November 2nd, we will be offering attendees are qualified to receive CFE credits from SAF. The credits will automatically be applied if you register for the event with the email associated with your SAF account. And then similarly, attendees are also qualified to receive CEU credits from ISA. If you are interested in that, please email forestc@msu.edu to receive the event code necessary to receive those credits. And with that, I will hand it over to Mark Bradford.
Thank you, Catherine, for the introduction. I'm just going to share my slides and double check with you that you can see them okay.
We can.
Okay, excellent. So, hello, thank you for inviting me, and thank you for joining us wherever you may be. So I think actually Colin in the second half of this talk is really going to take on the innovation. I'm hoping in the next 20 minutes to talk much more about sort of a little bit more old school and knowing the resource that it is, the forest resource that you're actually managing, knowing it well and establishing a sampling design so that when you go out to estimate carbon, it's meaningful and not a misdirection. So there are various key players in this work. All of the work that I'm about to present was led in terms of the research by Dr. Clara Pregitzer. She's currently Deputy Director of Conservation Science at the Natural Areas Conservancy, or NAC, in New York City, where they advocate for improved forest policy and practice around managing natural area forests. Also acknowledged here are various other key researchers and funders in the work that I'm presenting. So my big take home, so I'm going to put it out there up front. So this is a spoiler alert. You know how this is going to end. I'm going to make sort of the grand claim that to estimate forest carbon stocks confidently and to guide management that increases carbon, the very first thing that you have to do is accurately characterize your forest. That may sound really obvious, but I'm going to give an example next that shows that inaccurate characterization leads to incorrect carbon estimates and opens the door to management that degrades carbon stores and the forest in general. I'm a empirical scientist, boots on the ground. I go out, I like to take measurements. I like to be able to see the resource and I'm measuring and that the measurements sort of, if you like, dovetail with the observations that I'm making. So I think in order to convince you that of these grand pronouncements, you'll need a case study where we have a lot of on-the-ground data. So today I'm going to talk about New York City, although I also work in forests outside of cities. So when we think about New York City, most of us don't think about it as being a forested landscape necessarily. In 1492, it certainly was. And the city that has grown up today has sort of been built on and around the original forest land on these islands. Your kind of conception of how much forest there is in New York City today is sort of shaped by where you're viewing New York City from. If you take the picture here on the right-hand side, this was Inwood Hill Park, and it's one of 53 parks across the 5 boroughs, and about 10,000 acres of forest land in New York City. Now, if you're looking at that picture on the right-hand side, you're going to notice that the forest is very patchily distributed. And if we took a bird's eye view of New York City, it would look like this. So I'll just talk very briefly through this slide. Here are the 5 boroughs. Anything in gray here is impervious surface. Pervious surface are in these colors. About 20% of the land is non-forested or non-treed, and about 20% of the land has trees on it. Of that 20%, about 1/4 is in what we might normally term as forest, so closed canopy, close growing trees, and about 75% is in open grown trees, such as street trees, landscape trees, and backyard trees. This is important as a setup to think about the different kind of tree resources that we have within the city, because what I kind of want to really emphasize in this talk, that probably the most influential but under-discussed decision that you're going to make when you're managing a forest, including an urban forest, is what comprises your forest land for your measurement. So at the moment, many definitions of urban forest treat urban forest as synonymous with urban canopy. That means that all of these different tree cover types that you see here represented are included in our estimate when we go out and we make estimates of urban forests. And hence, once we define the urban canopy as synonymous with the urban forest, we tend to measure it as though it was a homogeneous resource. And obviously, it's a very different resource. Forested natural areas might require silvicultural prescriptions, whereas street trees might require arboricultural prescriptions for their effective management. So I'm going to make the claim that how you define urban forest matters because it dictates how you measure the urban forest. Those measurements shape your knowledge of the resource you're working with. And that knowledge and the overemphasis of the importance of big data, especially right now in decision-making, shapes policy and management, in this case, for the urban forest. So I'll give you the spoiler. In New York City, if you define the urban forest as all the green canopy, you threaten effective management. And so far, it's led to major underestimates of the number of trees in New York City, their native status, and how much carbon is stored. You might think about this is captured under a broader sort of data paradox that says even when you've got very large numbers of observations, if those observations aren't corrected in a manner that reflects your underlying resource, then you're going to reach conclusions where, because you've got a lot of data, you may have a lot of confidence in them, but that confidence is misplaced because your data don't represent what you'd actually like to measure. So in 20 minutes, I haven't got time to talk through detailed methods and results, but if you want to look at kind of initial estimates of carbon storage in the urban forest of New York City, you can go to this paper. It's open access and have a look through at all the results. But some of the major highlights from this particular paper are that when you look at prior estimates of urban forest stocks in New York City, you come up with 1.2 teragrams of carbon. A teragram is equivalent to 1 million metric tons of carbon. If you look at just the natural area forests, remember that's only 25% of the urban forest canopy. The estimate is 1.5 times greater than what people were estimating for the total city at 1.84 teragrams. And that's because these natural area forests within the city is where the bulk of the carbon is stored. If you dig a little deeper, what you find is that the oak hickory native type of forest to New York State is both the most abundant in terms of land cover, and it's also, because of how developed it is also the stands which have the most carbon per unit area. When you add that all up, you find that these native, well-managed forests that people like to recreate in and that we use for things like stormwater mitigation as well, have the greatest proportion of carbon, 0.82 teragrams of carbon, whereas exotic, more degraded landscapes that serve other services less well tend to have much less of the total amount of carbon. Now, one of the challenges in New York City is there are constant pressures, invasive species, invasive pests, and also just the weight of people that are using these landscapes. And so in order to keep them oak hickory, or to recover some of these successional hardwoods towards things like oak hickory stand types, the urban natural area forests, they need management. So if you remove management from these landscapes, you can go on a period of design of decline driven by things like invasive lianas, so woody vines that ultimately degrade the forest for all uses, including low carbon storage. Whereas in New York City, if you were to bring silvicultural prescriptions to the table, there's a lot of opportunity for management to sustain the current forests and actually improve the health of many of the forests in the landscape. And that improved health goes along with higher carbon storage. So when we think about the urban forest or the urban canopy in general, and I'm just going to move a couple of things around here, whether you support managing native dominated urban forests really depends on how you define the urban forest. So definitions right now that urban canopy is synonymous with urban forest has led to ideas and reports coming out that urban forests are somewhat unique from rural forests, and that in many urban areas that the forest is comprised of 50% natives and 50% non-natives, with the recommendation that we think about a brand new management regime for these particular forest areas. However, when you go in and target your measurement approaches specifically to actually characterize these different forest types, you get a very different picture, which is much more in line with the traditional silvicultural prescriptions that we might make for keeping these forests healthy. The advantage of working in New York City is you can explore these kinds of ideas because New York City has an awful lot of on-the-ground data. And the three main data types that I'm going to use here to try and convince you of this fact about how you define urban forestry and then how you go about measuring it really matters to shape your management prescriptions and your estimates of things like carbon storage, are these three data sets. One is an assessment carried out by the US Forest Service under the iTree system, which urban FIA are sort of building on and replicating, where 300 plots were dropped across New York City in a randomized design to go out and characterize the forest. New York City also went out and took a census. So they measured all 660,000 of their street trees. So we know very well like how many there are and also what species composition that they comprise. And then there was an effort led by New York City Parks and Rec, along with the Natural Areas Conservancy, to go out and put 1,100 plots across their natural areas forests, so they would have high density sampling within these really high value systems within the forest land. So if you sort of depict that iTree or urban FIA, and you look at where the plots are, when you drop those 300 plots again across New York City, the distribution looks somewhat like this. Myself and Rich Hallett from the US Forest Service were actually in charge of running the teams that went out and took these measurements. And of course, if you drop these points randomly across the city, what you can imagine is that you're generally measuring canopy types, which we wouldn't think about traditionally as forests, but would certainly be defined as urban canopy. So street trees, for example. By contrast, the 1,100 plots for the natural areas assessment went into all of these green areas So we could develop a really nice picture to estimate what the composition, carbon storage, and species composition was of these natural area forests. So a couple of highlights from just comparing these two different data sets and remembering that we've got the street trees to tell us what the rest of the different types of canopy cover looks like. If you go out and you use the urban FIA approach or the I-tree approach right now and randomly drop points on the city, a number of the species that you'll find, like Norway maple as a dominant within the urban forest, you'll realize from whether it's a basal area or the number of trees in the assessment that these non-native species are super abundant. If you go down and look at the street trees, similar species, Norway maple and pin oak as a native, both occur because they look very, very similar to street trees because of the way the points have been dropped. When we jump into the forested natural areas and look at the most important species within those systems, we find that they're all native and none of them overlap with the list about when we make broader definitions of the urban forest as synonymous with urban canopy, nor do they overlap with the dominant street trees. I prefer graphs to tables, so I want to show this slightly differently. These figures here show this is the urban forest assessment, the I-tree assessment. This is the natural areas assessment of those 1,100 plots. This is the street tree census of all 660,000 trees. There's no error around this because it's a census, not a population level estimate. And this tells you the proportion of species which are native from 100%, so native dominated canopy, to 100%, so non-native dominated canopy. What you see in all these little gray points underneath, these gray points are the actual plot on the ground 10-meter radius plots that we went out and measured in both of these assessments. So what you see is that when you drop these points randomly across the city, your urban forest has a mean that looks very, very similar to your street trees. Whereas if you go into the forested natural areas and you drop all of the points, what you find is then in general, we find native dominated canopies throughout. If you look at this slightly differently, and you look at forest structure, here, the density of trees per unit area against the mean tree diameter, you can see that the structure of New York City's forests, especially the native forests, tend to match very closely to FIA data that we can pull from New York State. If you want to read in detail about these kind of two different efforts, we had two papers led by Clara that came out in the peer-reviewed literature to support the work that we're showing. This one is available open access, as is this particular paper, sort of giving some guidelines about how we inform management and policy based on these kinds of measurements. But overall, what I really want to leave you with is that you set policy and management for, you set policy and you target management for the resource you believe you have. And that belief is really based on how you measure the urban canopy or the urban forest. So in this report here that we've jointly put out with the Natural Areas Conservancy and the Trust for Public Lands, we went out and we essentially went out and queried land managers across the United States and said, what are you managing for? And they pretty much unanimously came back and said, we're managing for native dominated forests. And a lot of that management means that we need to remove non-native species so that we can keep our forests healthy and steer their trajectories, while at the same time, because of these measurements, as the urban canopy being synonymous with the urban forest, just as in New York City, these folks were being challenged in how they were carrying out their management. Because the picture that you derive when you go out and randomly sample across these cities is of forest land, which is co-dominated by natives and non-natives. So people are asking the question and falling into the big data paradox and saying, hey, these big data suggest that you're managing for the very much for the rolling forest endpoints. Whereas if you go in and you stratify your management and target the particular resource that you care about, what you find is a very different picture. And maybe not surprisingly, those urban forest practitioners on the ground knew what they were looking at in the first place and have like now renewed emphasis, if you like, relying on large data sets, that they're actually managing for the right things. That management is important in New York City. It was up until fairly recently, it was illegal to cut a tree over 10 centimeter DBH, which really limited silvicultural prescriptions. And so we're using data sets such as these to try and push forward and make the case that many of these urban forests need to be managed in such a way where you can use silvicultural and not just apicultural management in these urban forests too, to maintain their native status, but also to grow the amount of carbon and maintain the amount of carbon on the landscape. I wasn't involved in this particular report, but the Natural Areas Conservancy and the US Forest Service just brought it out. So what I want to leave you with, I want to leave you with the importance of defining any forest land, but in this case, urban forest, to recognize diverse management needs. So two main sort of take homes from this is that if you want to estimate forest carbon stocks confidently and to guide management that increases carbon, you first have to accurately characterize your forest and beware of falling into the trap of defining your forest one way, and then that potentially having unintended consequences in the measurements that you ultimately take, and then the view that you develop based on those measurements of what your forest actually looks like. I'd argue that our accurate characterization leads to robust carbon estimates and opens the door to management that sustains and builds carbon stores and forest resilience. Thank you.
Thank you, Mark. And at this time, we will hand it over to Colin.
You may have to stop share. Oh, there we go. Sorry, I was going to say you may have to stop share for me.
All right, thank you, Mark, and thank you, Catherine. Can everybody see my screen, hear me, and everything? Excellent. So I'm going to jump right in here and pick up on a few threads that Mark left us with, but to set the stage and to provide the context here, this is work that we've been doing with partners in both the public and private sector in New York State over the last several years. And in 2019, New York State passed the Climate Leadership and Community Protection Act, which requires that New York achieve a net zero economy by 2050. And that involves reductions of emissions by 85%. And that other 15% of emissions is meant to be offset by natural and working lands, largely our forests. And this is a huge task based on current estimates by the FIA program. We're talking about more than doubling the size of the forest carbon sink in New York State by 2050, and not just doubling it by 2050 and walking away, but keeping it there and continuing to grow that carbon sink. And there's a lot of challenges and of course, opportunities around this. To support the state in doing so, we've been working to develop a map-based carbon accounting system for natural and working lands that is statewide. And really to bring this information into a map space, and we are not necessarily innovating all of the tools in doing so, but perhaps one of the innovations is to really integrate a lot of the functions that we need for decision support, both in the public sector in terms of policy and regulatory decision-making, as well as the private sector in terms of individual landowner decision-making, as Mark was referring to in terms of silviculture and arboriculture. And overall, to be able to tie those together with capable, effective, and efficient monitoring, reporting, and verification tools. And so, of course, the Forest Service FIA, right, is really the gold or platinum standard internationally, and it provides a tier 3 IPCC, right, a high level of technical capability to provide state level, and in some cases, county level estimates of annual forest carbon stocks and changes. Of course, you get to those sequestration estimates, those emission estimates through looking at changes. And of course, the FIA reports this data annually to the EPA's greenhouse gas reporting program, and that's based on the analysis of their field plot network. And there's about 4,500 plots across New York State, including the ones that Mark mentioned. State level stocks and trends are useful. You get these tabular results, you can compare them over time. And what we've seen in New York actually is a gradual weakening of the carbon sink over the last 30 years, which is not really the direction we want it to be going in. The problem is when we look at those tables, it offers relatively little actionable information at the scales that are relevant for decision-making or insights on where, why, and how the forest carbon sink may be changing, and especially in the Northeast, and especially in New York, which has the highest prevalence of invasives and forest pathogens in North America. There's a lot of reasons why our carbon sink is changing, and there's a lot of different actions that we might take to respond to that. So we set out to develop a statewide map-based inventory of forest biomass and carbon stocks to model and map historical conditions so that we could look at recent sequestration, recent emissions in terms of the forest sector. So additions to the carbon sink or a growing carbon sink, right, suggests sequestration is happening. A shrinking carbon sink suggests that net emissions are happening, right? And that's the whole stock change framework. So we wanted to be able to model and map historical biomass carbon stocks and incorporating land use land cover, and then apply that information in a geospatial or a map-based stock change framework to be able to estimate sequestration and emissions as defined by IPCC. And then be able to then also build the same framework or use that framework to observe the future carbon stock changes in a monitoring, verification, and reporting context. And as with Mark, I'm really going to try to cover a lot in a very short period of time. So it is a very, very, very high picture view. You might argue a satellite level view of all of this work, but to try to give you a sense of how we've done this soup to nuts so far and how the whole picture emerges. I'm happy to answer detailed questions. So one of the early infographics I produced to communicate this to policymakers and others was that we're mapping current biomass and carbon stocks. That's the green box in the middle. We're estimating the past retrospectively, and we're also monitoring and potentially simulating the future. Simulation is a great challenge. Our approach to this is actually really kind of a daisy chain of modeling exercises. So we initially, in this format here, this infographic is going to kind of be our roadmap through the rest of my talk. So we initially try to model the current biomass. We then model historical forest biomass. We convert biomass to carbon pools as best we can. Some of those conversions are good. Some of them are really real head scratchers, especially for soil carbon. Then we develop this stack of maps that tells us change over time consistently for the same space. And we use that to develop a map-based stock change analysis, which gives us a sense of carbon sinks and sources on the forest. And then we effectively implement that for statewide assessment and monitoring. That first step is really to use the FIA network across New York State. And where we have large footprint airborne LiDAR, this is light distance and ranging or airborne laser scanning. And we're training machine learning models on that field inventory, the LiDAR coverages and the geospatial variables. And then we use those models to map forest above ground biomass for the given LiDAR year at a 30-meter resolution. In all cases, we really spend a lot of time because, like Mark, I'm a field ecologist. There's no substitute for a walk in the woods and real measurements on the ground. But so we're always trying to compare our maps back to ground truth again in a variety of ways. And I only have one sign of that, but I'll show you that in a moment. The problem in New York is we have this random patchwork of LiDAR coverages collected by different agencies at different times. And this figure just shows that patchwork, and of course it's incomplete. So we already know that LiDAR isn't going to give us everything we need here. But what we are able to do is produce quite accurate maps of forest above ground biomass for different portions of the state that reflect that snapshot in time when LiDAR was flown. And so we have different portions of the state, different kinds of landscapes. This is southeastern Adirondacks, a contiguously forested landscape, including high peaks of New York. On the left here, you've got Cayuga and Oswego County. This is transitional landscape, but a lot of post-ag and current ag. A lot of apple orchards, important this time of year. We've got the Allegheny Plateau down in the southwestern and southern tier. And of course, we've got the lower Hudson Valley, which is a lot more of a mixed landscape. Unfortunately, though, of course, with all this LiDAR, we only have portions of the state and it's quite random. And so this doesn't get us all the way there, but what this does produce is quite accurate, some of the most accurate that at least we've been able to find in the literature in terms of these predictions of above ground biomass using the LiDAR. And one of the things that we do that the other groups have not done yet is we actually compare back our map surfaces. We tally these map surfaces up and we compare them to these small area hexagons that the FIA program produces. Now, these are much smaller areas than this sample, the design of FIA was meant to make predictions at. So they have some broad confidence intervals, but this is the most apples to apples comparison between an application of a map where you tally up a given arbitrary area like these hexagons versus what FIA would report based on its plot network. And what we found, for example, with our LiDAR-based maps is about 90% of our map predictions agreed within that confidence interval of FIA's design-based estimates. Now, you might doubt design-based estimates, and there's a lot of uncertainty that's packed into all of this that I don't have time to cover. One of the things that I think is interesting to note, and I don't know if you can see my cursor, but down here where our model misses is in these low biomass areas, which gets to Mark's point. When FIA goes out to some of these places, it doesn't qualify as forest for them, but our LiDAR definitely picks up vegetation biomass, and we're actually making predictions there. So this question of who's actually right is another question. But so we like these data a lot, but they have a lot of limitations. They're snapshots in time, they're incomplete. So we've leveraged them to train a second set of models based on Landsat. Landsat gives us all the way back into the 1980s. And Landsat's a program that we're pretty confident is going to continue into the future. And so we use these map predictions to train a second set of models, which has a whole slew of issues, but we use this to train a second set of models. This has been done by Matt Hudak and others out west to basically have a set of models based on Landsat imagery, which is freely available and gives us a full picture of New York State back in time and going into the future. And then we're able to produce annual 30-meter AGB maps from 1990 to 2009. And again, evaluating those back with the information that we have on the ground. So here's the LiDAR AGB map I showed you before, training models and ensembling these machine learning models, we're able to produce a Landsat-based map that looks like this, right? More importantly, we are able to run through time. So this is actually a movie. In the upper left there, you can see the target year, and this is moving through time, and this is going to loop, and I'll talk about it for a minute or two here, but you can see these changes over time. Now, some of this is related to imagery, some of it is noise. But when you hone in specific areas, and I've shown this to landowners, large industrial forest landowners, and they've been able to basically validate it by saying, yeah, I remember when we did this, and I remember when we did that, so forth. And it's a very qualitative validation. But what we're able to do is produce a time series of maps that tells a story of forest biomass and land use land cover change over time in a given area. And we have produced these for all of New York. Those are even less interesting movies to look at. So I'm actually going to do the opposite. And if you see this little diamond here, we're going to zoom into this area, which is adjacent to ESF's Huntington Forest. This is a working forest. And this movie is rolling through time. And on the graph on the right is showing you our estimate of total above ground biomass, essentially based on the average pixel values of metric tons per hectare, right? And what you can see as we move through time, it's going to cycle through again, start back over at 1990. We can see some changes, and particularly as we get into the time when the land changed hands from Finch Prine to the Nature Conservancy and then eventually to ATP, where they did a significant amount of harvesting. And then you can start to see the regeneration of that biomass taking place in these working forest lands. There's a number of issues with this that we've worked on. I don't have time to get into today, including this idea that it greens up before it grows up, which is this idea that you get green vegetation establishing back on the ground, and the models think that the biomass is recovering at the same rate. And I think most, if not all of us, know that that's not how this plays out. But looking at that signal and trying to understand how this is playing out is really valuable for us. But we can track this over time at a pretty high resolution. And we've ground truthed this against partners throughout the Adirondacks, over 500,000 acres of working forest land we have their harvest records for. So we're able to do a lot of tuning of the algorithms that are underlying a lot of this. So the next step is to convert biomass to carbon pools. And we're able to do this by modeling relationships between biomass and carbon pools based on FIA's own plot level measurements and training models and doing the best that we can with these. And this is an area where there's a lot more data that needs to be brought to bear. There are fundamental gaps in our knowledge, especially as it relates to soil carbon and forest soil carbon. These are gaps that even academics like Mark and I and Rich and others, like this is a huge area of work that needs more attention. But we've done the best that we can here to translate these biomass maps into carbon maps with the associated uncertainties. And that's what this picture on the right is showing. The upper left-hand corner AGB map is then used along with some other environmental geospatial kind of variables like topographic wetness index and mean temperature and precipitation, elevation, et cetera, and to give us some estimates of these carbon pools. And because we have this based on data that we have annually at 30 meters for 30 years, we can make those conversions and start to look at those carbon pools and potentially how they've changed over time. So just to show you, this is an estimate of the total forest carbon across New York State, with areas of developed shown in red, areas of water shown in white. There's a lot of other areas here that are shown really transparent, or I said blue, water and white, I meant blue, sorry. And the other areas are shown in white. And there's an inset map below that shows the land use land cover. So we are not making any soil carbon predictions anywhere where we don't believe there is tree cover. Now, our models are making predictions in some of the areas that like in the cities and in these red areas. For a variety of reasons, we're kind of holding them back, and we want to do some more work to improve them. But we are making wall-to-wall predictions, but we are pulling some of that data out because for a variety of reasons. And again, many technical questions I'm happy to dig into later or offline. The upshot of all of this is that we have a stack of maps. And with that stack of maps, we can then do an analysis on a pixel basis. We can segment that stack of maps into stands if we want to. We're doing some work along those lines, but we can do basic and some more sophisticated types of GIS analysis with this stack of maps on a pixel by pixel basis to understand things like net changes over time, growth rates, percent losses to disturbance, the timing of disturbance, the magnitude of disturbance, et cetera, and to be able to understand the processes going on there. So what this is moving all of this data into this fourth step, which is this map-based stock change analysis, which I believe, although there are some colleagues in Canada that have done some great pioneering work in this area, I believe this might be somewhat innovative for carbon accounting. So this map, I wrestled with this map forever. It looks better with a black background. I'm sorry if that's, but the color and some of the patterns pop better with this black background in New York State to show this is just the delta between 2019 and 1990 in terms of our estimates of above ground biomass, with areas in green kind of increasing in biomass and areas in orange decreasing. Now note, over a 30-year period, there's a range of gain of 30 or loss of 30 that is kind of masked out here. We're really looking for the larger changes, and some of that reflects our understanding of error around these model predictions. But to zoom in on this area of the Adirondacks, particular favorite area of mine in the North Country and Stillwater Reservoir, what I'm showing you here is a number of maps as we zoom in, where this is a matrix of both private land, working forest land. You can probably see it. I probably don't have to point it out to you where the parcel boundaries are there in those maps, as well as New York State Forest Preserve, Five Ponds Wilderness, Independence River Wild Forest. And you can see areas that we're estimating growth rates in. You can see areas where we've estimated biomass loss. Even though we have some sophisticated ways for estimating growth rates with non-parametric statistics and looking at biomass loss with different segmentation algorithms, at the end of the day, there's a great story told here just by subtracting the 1990 raster from the 2019 raster and looking at what those changes are. And you can see both large and small parcels. As somebody who has a close friend who has a camp down here, we've certainly seen the folks doing the harvesting in this area and explored some of this parcel. And you can see that there's also growth in this area. It's not strictly harvesting. When we convert this to carbon, the above ground live carbon, the above ground vegetation carbon stock change maps track really well and they make sense. What we found is the soil carbon maps all show declines, and that doesn't make sense. Although there are plausible ecological reasons for soil carbon pools in a place like the Adirondacks to decline, especially with warming climate, our models do not represent these processes at all. right? And so our models don't represent things that could be happening in reserve forests that would cause soil carbon pools to decrease. We largely expect them to be increasing. But of course, it's very possible that they might be decreasing, but we don't have the data and we don't have the right models to be able to make those predictions. So some of this is useful and some of it is grain of salt. The last piece is to really build this into being able to go forward. So our baseline approach here, right, we've really tried for monitoring, reporting, and verification, really tried to focus on accuracy, cost efficiency, and versatility, and a balance between those things. Our first version is based only on Landsat, FIA, and a suite of open source data and tools, right? So we're able to go from 1990 through the present day into the future, and we can go past 2050, right? If we're all here by then, hopefully we are, right? But we feel pretty confident that Landsat's going to be a thing in the future, and FIA is going to be a thing in the future. And we want to build a lot more sophistication and accuracy and capability with more remote sensing data like Sentinel, spaceborne LiDAR, satellite-borne radar, et cetera. But baby steps, right? So here's our baby step. And it's all built on stuff that is free and open source. So it is very efficient. It's very cost efficient and it's very versatile. So we're building this on R, Postgres, Google Earth Engine, Landtrender, obviously in these key data sources. The last thing I want to show you is the upshot of this, especially for the perspective of both public sector decision-making and monitoring, as well as local landowner decision-making and stewardship. We can take our maps and we have all of the statewide parcel boundaries from New York State, and we can burn those parcel boundaries on top of our maps and summarize any of our maps with those parcel level data. And so based on that, we can now start to assess as a first level assessment, not the final assessment. There's no substitute for boots on the ground. But as a first level assessment, to be able to go out and look at which parcels have the highest carbon density and need to be protected from deforestation, which parcels have the most potential for afforestation, which parcels are likely to sequester the most carbon in the next 30 to 50 to 70 years, and so forth. And so these assessments start to give us the ability to provide information that not only gives a big picture view to state decision makers when they have programs trying to incentivize different types of natural climate solutions for forests. They also mean that we have maps and data that we can provide to individual landowners as a first step to developing a management plan and to thinking about what are the right steps for them to take based on all of the values of the forest, not just carbon sequestration. And these are assets that may be useful, especially for consulting foresters as a starting point to work with some of these landowners. And we can do this for pretty small parcels. So you're not limited. Like, so I have people ask me all the time, well, I've only got 8 acres of forest. I'm like, that's 8 fantastic acres. But they're like, I can't be part of a carbon market. Well, maybe this can facilitate ways for co-ops to develop and other things to play out in the future. So I've said a lot. I think I'm out of time. I want to thank you all and apologize for the lack of technical detail, but hopefully you get the picture of what we've been doing and where we hope it goes. Thanks.
Thank you, Colin. And you were just at time. You did not run over. So we appreciate that. With our remaining time, we'd like to move to the Q&A portion of the webinar. We've been monitoring our chat feature and email. So we will start with some of those questions. And we'll start with Mark. Mark, recent studies have suggested carbon sequestration is much higher in edge areas. Did you take into consideration how much edge areas exist in the city? I'm
going to give the really short answer is that we didn't. But that with the plot density we had, that's something we could look at. With the iTree plots, it would be more challenging because they may fall across something like edge, and so your measurement there is for that whole plot. You can't essentially downscale from that particular grain of observation.
Next question is for Colin. Is any of the work on carbon pools focused on carbon in the soil? Some studies suggest that there's significant loss of carbon from harvesting, especially clear cutting. And it seems to be a significant factor for total carbon pools.
Thanks, Catherine, and thanks, Tim, for your question. This is so much of the work that needs to be done, Tim, is to really understand what is the fate of carbon in the soil under different land use practices, as well as when different kinds of land cover change occur, and how long does it take for those carbon changes to play out, right? So there's really a fundamental gap in our knowledge in many cases. There's more known about agriculture and agricultural practices, but really focusing on soil carbon. I think that we know the most in the boreal forest, and that's from all the work on climate and changing fire regimes and so forth. In our more temperate deciduous forests, like we have in much of North America, or at least Eastern North America and the Great Lakes states, very little is known. To your other point, yes, usually when there's a harvesting occur, or even a disturbance, where some or all of the canopy is removed, the soil tends to warm up. And with warmer soil and with dead tree roots in the ground, you do tend to see an increase in decomposition in the soil and respiration rate. So that's all the critters breaking down all the dead stuff, right? It's warmer for them. They've got more food to eat, so they're breathing out more CO2. So you get a flux, a bump of CO2 flux post-harvest. That is a bit more theoretical than demonstrated in the field. And to get back to Mark's point, we got to get out there and measure it. But it is something to be concerned about or to be aware of. On the other hand, if you have good regeneration taking place, a lot of times pretty quickly, roughly speaking, within 10 to 20 years, the net sequestration rate of the regenerating vegetation is going to far outpace that bump. And then again, it's also shading the soil now, right, which cools it back down again.
Thank you, Colin. I'm going to come back to you, Mark, with this next question. Could you provide examples of how forest management has been negatively impacted by inaccurately characterizing forests?
In terms of, so I think I was hoping that I would get that across in my talk overall, that, one of the biggest, I'm actually a soil scientist based on my expertise. So the soil carbon question, I feel like a politician if I dodge. So I'll go back to that forest management. I went into New York City to actually measure their soil carbon around the Million Trees Initiative when they were putting 1 million trees into New York City in 2009. And very rapidly, as I started talking to the folks that were managing the land, realized that their challenge was the broader narratives around what your forest composition was and what your forest looked like. And so the reason why we had things like the Million Trees Initiative were because of the efforts to make things like urban canopy and urban forests synonymous. It brought huge amounts of funding in for green infrastructure into cities. So I think it had real benefits. I think the unintended consequences was that we then started measuring urban forests in that way. So what we were finding in New York City, and then in other places we went on to that, is that management budgets were being cut for managing healthy natural area forests, because the urban forest practitioners wanted to manage for native dominated stands, which is what they saw there on the landscape. And yet the large data narrative that was being developed and was dominating at that time was coming back and saying, actually, these are novel forests. These are forests not like any rural forest that you would see. They're 50% non-native, 50% native. And so really that should be your management objective. So it makes life difficult for folks. So I think steering the narratives in terms of what you're actually wanting to manage for and making sure your data are collected in that way is really important.
Thank you.
I'm going to add, if you want me to step just very briefly outside of cities, I'm going to say that if we look at things like, which Colin's work is directly relevant for, things like improved forest management right now and various carbon markets, how we collect those on the ground data, which data sources we use to set baselines and to follow trajectories of forest change. There isn't, if people go into those voluntary protocols or even the regulatory ones under CARB, the California Air Resources Board, you're going to find that it's very light on details in terms of how you go out and take those measurements. Even when you find the proprietary methodologies, they're also very light. What that's doing is creating uncertainty and therefore lower confidence that as we go out and we measure those forests, are we actually accurately capturing the change in carbon, which has been the change in carbon from when we've used improved forest management practices. And you know, one of my aims is to work around things like those methodologies, to bring in a set of methodologies that increases confidence, to make sure that those revenue streams are flowing to keep forest lands and protect the broader interests of forests in those communities and those areas.
Thank you, Colin. I thought we could go back and talk about the soil carbon stock changes. I know you mentioned that they were declining in the models. One question was, how do you validate the data that you're using? Is there reliable soil data that you can compare your results to see whether your results are, just missing a piece of what we're actually seeing in the forests?
So yeah, I mean, one of the reasons why the models are not great there, and they're the ones that are the most precarious, is that measuring soil carbon is very time consuming and expensive, and they only do it at a very small subset of the FIA plots that are out there. And so you have a limited amount of data to work with. And of course, as most folks who spent time in forests know, your above ground volume, your above ground biomass is not necessarily a good predictor at all of your soil carbon. And your land use history, your hydrology, your climate are much better predictors of soil carbon. And we're working on some other modeling approaches to try to get at better soil carbon, but so is everybody right now. I think it's a real tricky thing, and there's so many questions around this. So, but to answer your question, we need that data to train the models, and then we can go back and compare and see how our model predictions, right? Anytime we do this model training, we hold out 30% of the data that we have, right? And then compare that to what our model predicts, right? So there's always training and testing. When you have very small data sets like with soil carbon, we can do some cross-validation procedures that help us leverage the data as much as possible. So there are certainly some techniques that we've tried to use, but the short answer to your question is we don't have great independent soil carbon data that allows us to really evaluate these maps, and they're out on a limb there. And that's why I don't have a lot of confidence. And I mean, I think that the soil carbon maps are plausible. They're just as plausible as others I've seen. And we do know that we're making some improvements over predicting like a mean value, right? Which over a null model. But when we look at the stock change based on that to see soil carbon stocks widespread declining across the state, that doesn't pass the smell test for me. So I shared them with you in the honor of transparency, right? We have a lot of work to do there, but there's so much more knowledge that needs to go into it. So short answer is we don't have a lot to validate them against. We have better validation information for other kinds of components of what we're predicting, and including stock changes related to forestry and land use change. And Catherine, I hope I'm not misbehaving by answering a few questions in the chat, but maybe I shouldn't do that. Sorry.
That's okay.
Couldn't resist.
That's okay. Mark, I think, at the end or in the beginning of your presentation, you mentioned that there is an over reliance on big data. And I wondered if you could speak to that. And is it possible to improve estimates while still using big data and then, applying native natural area forest weighting factors, things along those lines?
So I think, no, I think it's actually a great question, and it spans across fields. This is not something that we're just dealing with in forestry or in carbon accounting. We're seeing this in medicine, epidemiology, multiple other areas. So actually weighting, interestingly enough, so Colin mentioned as well the big data paradox. Weighting often doesn't save you. There was a large study that recently came out around COVID showing that hundreds of thousands of observations do much less well than 1,000 well-targeted observations each week in understanding things like vaccination rates. So much of this comes down to essentially, much of this comes down to domain knowledge, which is a real jargon term that people use, but it's, as Colin emphasized it multiple times, it's boots on the ground and knowing your resource. So I'm a huge proponent of big data. I think there are so many questions right now that we can't address. Soil, change in soil carbon under harvest practices being one of them that we don't have a lot of confidence in because of lack of measurements and ways to do it economically. So I think big data are a huge opportunity. At the same time, they're viewed as a huge risk if they outcompete at the table that local knowledge, that knowledge of the natural history, that knowledge of practice. And so just bringing them back in and making sure that they have a seat at the table, but their voice is not super loud, I think is really important. You know, I could really bore people, but I'll end on one point. The American Statistical Association has never told the general public or science how to do business. And in 2016, they made a statement which they released and told us how to do business. And they had two main reasons for that. And one of them were their fears that big data would be used to reach incorrect conclusions, whether you're managing for people's health or whether you're managing the natural environment. And so gave guidelines on how to improve.
Colin, did you have something to say in response to that?
Yeah, I mean, I think sometimes we're using, you know, one of the things that always occurs to me, for years, I've been the guy on graduate committees and stuff who's worked with the remote sensing engineers, because with all due respect to my friends across the quad, like I've actually been in the woods, right? So I know what things look like, and I know, and I always used to think, you know, using some of these big data tools, machine learning algorithms, all this fancy stuff. And then on the other side, no one questioned the allometrics that we use to take a diameter at breast height and a height measurement, which all of us know if we've done in the field is pretty fuzzy, right? Height measurements from the ground with a clinometer are pretty fuzzy. And to take those and to turn that into a biomass estimate, that is a huge modeling exercise in itself with a great deal of uncertainty. And those of you who have gotten wonky into this, as I have over the last few years, know there's different sets of equations for doing that. There's different sets of equations for urban trees. I know that Dave Nowak has worked on over the years, as opposed for trees growing up in closed canopy. There's uncertainty everywhere you look. Everything that I just shared with you, we're modeling on models. Like, that's breaking every rule I was ever taught, but we're trying to do it in a way that we're not losing track of uncertainty. We're trying to minimize the error propagation where it exists. And we're trying to be pretty clear-eyed about, let's not let the perfect be the enemy of the good. And I think what we produced is good. And I'm seeing a lot of questions in here, so I'll try to answer all of them very briefly again. We are comparing our maps back to FIA's predictions at a plot to pixel scale, which is a very challenging thing for a map to do. And then they're aggregating up at multiple scales. So we'll have a paper coming out soon that describes some of this, but we're using Rachel Riemann's approach for comparing map surfaces back to FIA network. And we're also comparing our maps back to the Menlove and Healy hexagons, which I understand were somewhat controversial within FIA because there are only 6 or 7 plots goes into each one. And that's a much smaller sample than the FIA's design was meant to handle. And so, but it does give us a real apples to apples comparison of what our maps describe for this whole area based on compared to what FIA would estimate for that whole area. We're also working with land trusts and landowners, industrial working forest landowners, as well as land trusts across the state to produce independent validation data. It's completely independent of all of our modeling to see how well we're doing. I'll mention that Michelle Brown at Nature Conservancy of New York took some of our earlier model estimates and compared them with her team to some of their inventory data from their parcels across the state, and found that our error rates were in the order between 1% and 11%, which was wildly better than I had ever imagined. But I do think that we have something that's viable and worth building on. But is there room for improvement? Absolutely. As I teach my students, all models are wrong. Some models are more useful than others, right? So I just saw a number of questions about validation, so I'm hoping that addresses some of them. I'm happy to follow up with anybody.
And we've actually reached that 4 o'clock mark, and we are running over a little bit. I wanted to say thank you to you both for sharing your information and for your time. Again, the webinar will be recorded and will be available on our website, and slides will be posted in a few days. I believe both Colin and Mark mentioned that you can feel free to reach out if you have questions and would like to discuss their research further.
Thank you, Catherine. Thanks to FCCP and to SAF and to everybody who was listening.
Yes, thank you all.
Have a good day.